In this video, I want to introduce a concept which is extremely important in applied mathematics and which will be the motivation behind many more videos on inverse problems in the future on this channel. So we will see the notion of ill-conditioned linear systems and why they are allowed or they could amplify noise and why this is a big problem. So as a motivation, let's take a look at this introductory picture that is taken from a paper that I'm citing in the description of the video. And in this case, what we took is a bunch of points in the plane that are drawn from a distribution that is essentially focused around an S shape. And what we did then is just apply a certain matrix that has some properties that make it nice for my purpose here. And that's A here, so it's just a linear operator, and that's the notation here. And then we added some random Gaussian noise. And this is what we call Y. So each point in this plot here is obtained through the application of A to the points here, plus some additional noise, and you get something like this. So the S shape is very well distorted, and it's also perturbed through noise. These could be observations of some phenomenon that we are provided, and our goal is not necessarily to work with this Y. We don't really care of Y. What we actually care of is X. And a natural thing to try, natural approach to pursue would be to try to invert this known forward map, this known linear map A, and apply to the observed points, the observed data. And if we do that, we get something which is very, very far from what we are hoping for, what we are aiming for. So if you invert A, which is an invertible matrix in our case, and you apply it to Y, which is this perturbed and noisy data, you don't recover anything close to the actual target. And in this video, we're going to see why this is the case and why this is a problem for real applications. So as a simple warning example, which is just to play a little bit with what we saw at a high level in the previous introductory slide, let's think to a matrix A, which is 2 by 2 as in the previous slide, and it is quite a simple diagonal matrix. It is with entries Y and epsilon on the diagonal, and epsilon is 10 minus 3. And let's say that we want to solve a linear system. B could be, for example, a source term we know, some data we know, like the Y we had in the previous slide. And what we can do is just focus on this linear system. So AX equal B, and we are looking for X. We know both A and B. So we can easily solve this diagonal system because we can just say X1 is equal to B1, since there is a 1 here. And X2 is nothing else than B2 over epsilon, because epsilon is scaling X2 here. So this is a quite simple system. Now what happens if we don't know if the second entry of B is exactly B2 or if there is some other perturbation? And we work with B tilde instead of B, which is B plus delta B. Since we don't have access to B, we are solving AX is B tilde. So we call the solution X tilde, and it's just the inverse of A applied to B tilde. Now, of course, the first component, X1, doesn't change, but what changes is the second entry, because in this case, it will not be just B2 over epsilon, but it will be B2 plus delta B2 over epsilon. So if we call delta X2 the difference between the two second components, you see that the gap, the variation is equal to delta B2 over epsilon. And this scales with 1 over epsilon, so the factor 1 over epsilon is 10 power 3, so we have a relative variation in the solution, in the recovered solution, because of this noise, which is proportional to 10 power 3. So a very tiny perturbation, it could still impact considerably the result here in this case, and this must be because of some bad property of the matrix A. So what I want to characterize is why this matrix is leading to such a bad behavior in this case, and why this is unfortunately unavoidable in many real-world applications. A little informative calculation, which is essentially a generalization of what we saw before, is that if we have two linear systems based on the same source term, in one case it is clean, B, and the other is noisy with some perturbation delta B. What we can see is what happens to the difference between the two solutions, how much the solution does change. So if we take the difference between these two vectors, we get by collecting A times X bar minus X is equal to delta B. Okay, so I took this minus this. You can see that the distance between x bar and x in the L2 norm is bounded by the spectral norm of A minus 1 times the gap, the norm of the gap. Similarly, you can do the same just focusing on this system and get that the norm of B is equal to the norm of AX, and this is upper bounded by the spectral norm of A times the spectral norm of X. And hence we have a control from below over the norm of X given by the norm of B, the Euclidean norm of B, over the norm of the forward operator A. So the idea now is to use these kind of estimates to get a bound on the relative variation of the solution because of this perturbation delta B. Relative means the norm of the difference over the norm of the target solution. And just combining these two results, we get this ratio can be bounded from above by the product of the spectral norms of A and the spectral norm of the inverse of A times the relative variation of the source term B. So you have how much B is perturbed because of noise or because of something else over the actual value, the actual magnitude of the original source term. The problem is that this is not always possible to guarantee because it depends on how good is the matrix A. So how small is this object here? So this product here is sometimes or often known as condition number of the matrix A. And since we have been using the spectral norm in this case and the Euclidean norm for vectors, this is the condition number based on the L2 norm. So sometimes you will see a kappa of 2 of A. So it's just a definition. In this case, kappa 2 of A is equal to this product of two norms. Now, the important aspect here is that we need to provide an interpretation of this result, which is that, of course, this is just an upper bound. So it's a pessimistic bound, possibly. But it's just the best we can do. And it tells us that if the condition number kappa 2 of A or kappa of A is large, then in principle we could have a very large relative variation in the solution, even though we have a small relative variation in the source term. So even though this object is small, if kappa of A is large, we could have said that this upper bound is fairly large. So this is actually explaining a bit more what is happening here. And you could take a look at the condition number of this simple matrix, because the inverse is easy to compute. It's just 1 and 1 over epsilon. So the condition number in this case is actually equal to 1000. So it's a very large condition number. And hence you could have that a small perturbation in the source term because of noise is extremely amplified just through the inverse of the matrix A. Why is this a problem? Of course, it's a problem in this particular case of solving linear systems. But there's much more behind this, in the sense that inverse problems, which is a subject area in applied mathematics, which has applications in several different fields, from medicine to image reconstruction in museums, hospitals, and so on. So a typical inverse problem is to reconstruct the clean signal based on some noisy and perturbed transformed data that we have observed. So an example you could keep in mind is the task of reconstructing from this image of a coffee cup, which is noisy and also blurred. And blurring is actually the action of a matrix over the image. And from this signal here, which is very low quality, low resolution, we would like to reconstruct the high resolution image we are interested in, so the actual picture. So in this case, what happens is exactly similar to what we had before. We would like to invert the linear operator that is blurring this image, that is adding this motion blurring over the image. We have exactly the problem we had before, because this is noisy, and if the forward operator is ill-conditioned, meaning that the condition number is large, as it usually is in these kind of situations, we are not able to simply invert that known linear operator to recover the high quality image. And that's why there's a whole field dedicated to this kind of problems that attempts and successfully attempts in several situations to address this limitation and finding different ways to reconstruct this image here without directly inverting the matrix. Because we saw that directly inverting the matrix is not so clever in the sense we will amplify noise and perturbation. So we will never reconstruct something as good as this. So we need somehow to find better ways to do this, to reconstruct this image. And this implies using different algorithms, using regularization strategies and so on. And I will try to dedicate some space in my channel to these kind of problems, especially also inviting maybe some guests that are more expert than me in some of these areas to try to address some of these approaches. So this is everything for this video. If you have any questions on what I've explained, let me know in the comments, or also if you have any suggestions for future videos, let me know. Otherwise, see you in the next one. Bye.